Hey Pre-Calc students, in this video we're going to cover polynomials. We're going to review polynomials that you've learned in previous classes, and we will also look at features of polynomial functions from their equations and from their graphs. Okay, the first thing that we want to talk about is what a polynomial is. So polynomials are any function built by coefficients, variables, and positive whole number exponents. On the left side, I have three examples of polynomial functions. So my first equation that you will see is f of x is equal to 3x to the 5th power minus 4x to the 4th power minus 2x to the 3rd power plus 5. This is a polynomial. We call a 5th degree polynomial, so 5th degree because of that 5, a quintic. And anything that has more than 3 terms, we just call it a quintic polynomial. For my second function, g of x, I have 3x squared plus 5x minus 10. Because of the second degree, we call these quadratics. And this polynomial has 3 terms. So even more specifically, calling it a polynomial, I can give it a trinomial name. A trinomial is a type of polynomial. Capital G of x equaling negative 5 is what's called a constant monomial. Mono meaning 1, and then constant because it doesn't have a variable, so it doesn't vary, it's constant. And my last example of a polynomial that I have is this h of x s function. And just worth mentioning that the variables kind of don't really matter as long as we're talking single variable. And then this is a polynomial. If I were to multiply this out, this is currently in factored form. But if I wanted to put it in standard form, I could multiply it back out. So I'd get 6s to the 3rd power minus 3s. And I could call this a cubic. And because it only has 2 terms, I could call this a cubic binomial. So all of these are polynomials you've seen before, just kind of understanding what polynomials are. On the right side of this screen, these are things that are not considered polynomial, but kind of look like polynomials, and we'll talk about why they're not. So first, this positive whole number exponent deal is really important when we're talking about polynomials. So for instance, my first function, h of x, is not a polynomial because I have a 1/3 exponent. A 1/3 exponent would keep this function from being considered a polynomial function. In fact, a 1/3 power is the same thing as a cube root. So this function would actually be a cube root function. And then my next one is not a polynomial because, again, it has to be a positive whole number. And I have an exponent of -3 here. And for negative exponents, these are actually a certain type of rational function. So again, you can't have fraction exponents and you can't have negative exponents. They kind of look like polynomials, but they are different functions. Polynomials with one variable are always a smooth, continuous line, and they can have the following features. So I have a graph. I have a 4th degree, so 4th power, x to the 4th power minus 2x to the 2nd power plus x is graphed. This polynomial, if we wanted to keep practicing our names, we call a 4th degree a quartic. And because it has 3 terms, we would call this a quartic trinomial. And it can have the following features. So you can see the graph of this quartic trinomial. It is a type of polynomial. When I say zeros, when I talk about zeros, I'm talking about x-intercepts, also known as roots. And this quartic trinomial, you can see, has some x-intercepts, 1, 2, 3, 4 x-intercepts on this graph. If I am talking about the y-intercept, okay, polynomials can have y-intercepts. In fact, all polynomials will have a y-intercept. When we're talking about end behavior of a polynomial, so all polynomials will go to some type of infinity. In this case, this graph, both ends go to positive infinity, which we'll talk more about end behavior in some future examples, but all polynomials have in behavior. And then also all polynomials have some type of minimum and some type of maximum. So this graph specifically has an absolute minimum down here, and it also has another little relative minimum right there on the graph, and then it has an relative maximum right here. So lots of features on this graph that we can talk about, and we're going to talk specifically how do we find all of these from the equations. So the polynomial can be in a couple forms. So it can be in standard form, it can also be in factored form. And here's a list of reasons why we would want a polynomial in standard form. So in standard form, you can find the following features easily. So the first thing is the degree, which is our largest exponent. So that's where we get names like a quadratic or a cubic or a quartic. So the degree is easy to find in standard form. So too is the leading coefficient. The leading coefficient is the coefficient of the term with the largest exponent. That would mean leading coefficients, usually we use those to describe whether the function is positive or negative. With the degree and the leading coefficient, you can determine the in behavior of the polynomial. You can also tell in standard form how many maxes and minimums the graph might have and how many roots the graph might have. Again, these are potential numbers, not guaranteed, but you can kind of roughly start to get a look at what the shape of this graph would look like. Let's do some examples. Okay, when determining in behavior kind of falls into one of four categories for all polynomials. The first thing that you always want to know when you're determining in behavior is what type of degree you have. Your degree can be an even number or an odd number. You can also want to determine your leading coefficient. Your leading coefficient is really important whether it is positive or negative. To look at each one of these scenarios, we have four kind of cases going on, right? You can have an even positive or an odd negative. There's four different kind of cases. So the best way to do this is to look at examples, and then we'll make general statements about the in behavior. So the first examples that we're going to look at are even and positive functions. So even is going to have a largest degree of any even number. And positive coefficients, we want the first number in front of the term to be positive. Let's see some examples. Okay, I have three examples. The first one is y equals 7x squared minus 3x. This is a positive even degree. Positive because the 7 is positive, even because the highest exponent is a 2. The second example I have is y equals x to the fourth minus x squared plus 2x minus 1. This is also positive because the leading coefficient is 1 and the highest exponent is 4, making it an even degree. So positive and even. And then my last example is 0.2 x to the 6th power minus x to the 5th power plus whatever. That doesn't really matter. Again, the point is the leading coefficient positive? It's 0.2, so yes, that's a positive number. And is the degree even? The biggest exponent that I have in this problem is 6, so it is all even. So for these three different examples, you can kind of start to see what is similar about them is always going to be the ends. Notice the ends are all going up. And so because all these ends are going up, what's going to happen is I can make a definitive statement about my end behavior when I have an even degree and the leading coefficient is positive. The first end I'm going to make a statement about is as x approaches positive infinity. So as x goes to positive infinity, all of these graphs are going to positive infinity. So as x approaches infinity, the y approaches infinity. On the other side, as x is approaching negative infinity, the functions are still going up. So as x is approaching negative infinity, that end is still going up. So as x is approaching negative infinity, y is approaching Still positive infinity because those ends are going up. Okay, I'm not going to show graphs for even and negative, but I do want to think really quickly about what would happen to these graphs if I were to make the leading coefficient negative. We've been learning about transformations on graphs, and to do a negative outside of the graph, all it's going to do is it's going to reflect all these graphs upside down. So instead of the ends both going up, these ends are going to both go down. So we can write our end behavior from there. We can say as x is approaching positive infinity, the ends will go down. So y will approach negative infinity. And same thing when x approaches negative infinity, that end will also go down. So y will still approach negative infinity. Okay, I'm going to delete these graphs and then show you some odd and positive, and then we'll talk about reflecting them to make them odd and negative. Okay, for these three odd positive polynomials, I have a positive cubic. That cubic 3 is an odd number, so that makes it odd. I have a 2x to the 5th power, again, just focusing on the leading coefficient. 2 being positive, 5 being odd, and again, only caring about the highest exponent. And then here I also have a 2x to the 1 power. When there is no exponent, the exponent is 1. 1 is an odd number. So all of these have similar end behaviors. In other words, the positive side is going up and the negative side is going down. That's true for all of these graphs. Positive side going up, negative side going down, positive side going up, negative side going down. So for all of these graphs, we can say that as x approaches positive infinity, well, the positive side is going to go up to infinity. So y is approaching infinity. And the negative side, as x approaches negative infinity, that side is going down. So y is approaching negative infinity. And similar to the last one, not pulling up graphs for the negative ones of these values, just understanding that it's going to be a reflection. So instead of a positive side going up, now our positive side will go down. Positive side will go down and our negative sides will go up. So again, reflecting that across the x-axis is what happens when you make a function negative. So when the leading coefficient is negative, as x approaches positive infinity, our y's are going to go down to negative infinity, and as x approaches negative infinity, our y's are going to approach positive infinity. Again, just a reflection of what's happening on the positive side. As well as finding end behavior, you can use your degree to find turning points and zeros. So a polynomial with a degree n has at most n minus 1 turning points, and a polynomial of degree n has at most n zeros. An example of that would be pulling back this example that we've already seen. We have x to the 4th minus 2x to the 2nd plus x. This is in standard form. I can quickly see my degree is 4. So my turning points is going to be 1 less than that. So n minus 1 means I'm going to have potentially 3 turning points. A turning point is an extreme value, so the maxes and the mins. And if I count them, I have 1 minimum, a maximum, and a minimum. So that is a total of 3 turning points. And then the zeros, I can have as many as n zeros. So if my degree is 4, I could have 4 zeros. Zeros, again, are your x-intercepts. And if I count my x-intercepts, let me switch colors. If I count up my x-intercepts, I have 1, 2, 3, 4 x-intercepts, which again, you're going to have whatever your degree is, you'll have that many zeros. It's not guaranteed to have that many zeros. This is an at most. So a fourth degree will have at most 4 zeros, and a fourth degree will have at most 3 turning points. Okay, so we've been talking about standard form and the benefits of standard form, but there's also factored form, and we do have benefits in that form as well. The benefits of factored form is it allows you to find zeros easily. It also helps you understand if at these zeros, these x-intercepts, are they going to cross the x-axis versus touching the x-axis. And then also, it's best to use factored form when you're trying to write an equation of a polynomial, especially if you have the graph. So we'll take a look at some of those examples of finding zeros from factored form, understanding crossing versus touching using factored form, and then writing an equation using factored form. So one factored form benefit is it allows you to find the x-intercepts. To find your x-intercepts, you're going to set all your factors equal to 0. So to find, again, your x-intercepts, you just take each factor and set it equal to 0. So my first factor is 4. If I set 4 equal to 0, there's nothing to solve for, so this factor does not have an x-intercept, so there's no x-intercepts that come from there. My second factor, x plus 4, if I solve this, I have an x-intercept at x equals -4. And if I solve this equation, I have an x-intercept at 5. So the factored form, the benefits of factored form are the factors show you your x-intercepts really quick and easy. So if I were to graph this polynomial, I would have x-intercepts at -4 and 5. Showing that on the graph, I have my equation 4 times x plus 4 times x minus 5 squared. I have that graphed here, so you can see I have one x-intercept at -4 and one x-intercept at 5. Again, setting the factors equal to 0 is a great way to find your x-intercepts, also called zeros, also called roots. The next benefit of factored form is the multiplicity. So multiplicity describes the number of times a factor occurs in a polynomial. An odd multiplicity means that the graph will cross the x-axis. And an even multiplicity means that the graph will turn on the x-axis. Best way to show this is talking about my example here. So I have this function f of x equals x to the 3rd power, x minus 2 to the 4th power, x minus 4, there's no exponent, so there's an understood 1 there. So x minus 4 to the 1 power, and x minus 5 to the 2nd power. Talking about each one of these x-intercepts, if you will take a second, pause the video, and find all x-intercepts for me. Okay, I have mine in 2 different colors because I want to show the difference between the odd and the even multiplicity here. So I have x cubed and x minus 4 in blue. The reason why I have these in blue are the multiplicity of the first one is 3 and the multiplicity of my second x minus 4 is 1. So if I look at these x-intercepts on the graph, here I have an x-intercept at 0. Here I have an x-intercept at 4. At these x-intercepts, you'll notice that the graph is crossing the x-axis at this point. The other color that I'm using is red. The reason why I'm using red is because x minus 2 to the 4th power, 4 being an even number, and x minus 5 to the 2nd power, 2 also being an even number. If I find these x-intercepts, 2 and 5, you'll notice that when the function gets to the x-axis, it turns on the x-axis rather than crossing. So creating a little bit of a maximum here because it's turning and a minimum here, it's turning at 5. So if the multiplicity is even, the graph will turn on the x-axis, and if the multiplicity is odd, the graph will cross on the x-axis. Our final example is writing an equation. We're going to use factored form to do this. So the first thing that we're going to do is we're going to use our x-intercepts to create factors. I'm going to also add a caveat to that. Not only are we going to use x-intercepts, but we're also going to use multiplicity. Then we're going to use a point on the function to find any vertical stretch on the graph, and we'll talk about why this is going to be important. So step 1, we want to find our x-intercepts, and we're going to use these to create factors. I see 2 x-intercepts on this graph that I have provided. I have a -2 and I have a +5. To create my x-intercept, I'm actually going to, you can think about this as like working backwards. So I know that my x-intercept is at -2, and I know that my x-intercept is at +5. I want to get 0 on one side, so you can just think about adding 2 to both sides and subtracting 5 from both sides. So these are my factors. However, I also want to use my multiplicity. One thing I notice, and this is special, is that this at -2, my graph turns on the x-axis, so I need to have an even multiplicity here. I'm going to give it an exponent of 2. That's the smallest even number. I also notice that it's turning, and then the other one is crossing, which means I need an odd multiplicity, so I'm going to use an exponent of 1. Again, usually you use the smallest possible even and odd numbers when you're trying to write your equation. So right now I have a rough equation of y equals x plus 2 squared times x minus 5. Now, if I check my work, and I'm going to do that, I'm going to graph this function, and this is not going to be quite the right graph, and we're going to talk about how can we fix this by using a vertical stretch. Okay, the reason why I wanted to check the graph is I have created the correct right x-intercepts, so I do have a bouncing motion or a turning motion here at -2, and I do have a crossing at 5. So my x-intercepts are correct, but the issue is that currently, as I type in this equation right here, I have a y-intercept at -20. So what I want to do is I want to create a vertical stretch on my graph such that I can, 1, reflect my graph so that my y-intercept will be positive, and then I'm going to stretch my graph from 20 to 100. The best way to do this is to create an unknown. So step 2, I'm going to do this step in green. I'm going to create an unknown vertical stretch. So I'm going to say this is y equals some vertical stretch on this equation. Then I'm going to select a point and use that point to find a. So the point that I'm going to use is the point that's being provided. I can see my y-intercept is at 0, 100. So I'm going to let x be 0 and y be 100, and this will give me values to plug in so that I can solve for a. So the first thing I'm going to do is I'm going to simplify all the things that are being multiplied to a. And now I'm going to get a alone by dividing both sides by -20. So now I can see that what I really need is a vertical stretch of -5, which is also a reflection and a stretch of 5 to make this polynomial match the graph. So my final equation of this graph is going to be y equals -5 x plus 2 squared times x minus 5. That's it for this video. We will do more practice with this in class tomorrow.